Okay, so let's get the recording going here. So today's topic, we've got a library of functions, and then we're going to perform transformations on these functions. We want to talk about our building blocks. We did function evaluation last week, and we saw that not only can we evaluate functions on numbers, but we can plug in other expressions into functions. And those other expressions, in many ways, are going to correspond to transformations and more general compositions of functions, which we'll get into next week. But we need, in some sense, our library of functions, our building block of functions, so that we can build new functions out of. We want sort of this basic graphs of our very basic functions, and then we want to be able to build new functions based off of those. So let's go through those real quick. Hopefully they are all review, and you guys have seen them somewhere before in your mathematical curriculums. So the first function we want to talk about is our basic linear function. That's just f of x equals x. In general, we'll have mx plus b as a nice linear form. Sometimes we'll have point slope forms for lines. But right now, all we really care about is just this guy. This will be our basic building block for all linear functions. Basic properties is, well, it's a 45-degree line through the origin. There's not much else to be kind of said with that. With all these graphs, I recommend graphing like 2 or 3 key points on your graph. You don't have to be incredibly precise in general, but you should try to at least precisely graph 2 or 3 points based on your scale. So 45-degree line, going to go through the point 1, 1, negative 1, 1, and then 0, 0 is our third point. And just a basic 45-degree line. We have our squaring function, which will lead to our general quadratic functions. So f of x equals x squared. And with this guy, key points, so it's going to go through 0, 0. And if you want, we can always make a table for all of these guys. So our x, y, 0, 1, minus 1 are always good points. So 0, 0, 1, 1, and minus 1, 1. And our parabola is going to look something like that. We've got our cubic function. F of x is x cubed. It's going to look similar to a parabola, except the left side is going to be flipped upside down. So if we plug in our point 0, 0, 1, 1, when I cube minus 1, we'll get minus 1. So the key points we draw for this guy, 0, 0, 1, 1, minus 1, 1. And since it's a cube, what's going to happen? It's going to look flat at the origin, and then the right side's going to go up. It's going to get pretty steep pretty quickly. And then the left side's going to curve downward and then decrease pretty quickly. One thing I like to call, I kind of like call 0, 0 as like a base point. It's a very good starting point for each of these. And then you can always graph the other points relative to that starting point. Because as we shift things, what we're going to do with these transformations is take these graphs, shift them up and down. We're going to stretch, compress, flip, all these kind of things. And so you can kind of track what's happening to this base point under these transformations. And so like if we were graphing a cubic, wherever the base point goes, the other 2 points I know are going to go right one, up one, left one, and down one, if there's no stretching or anything like that to do. And we'll see how to take care of that when that arises. Our other 2 function classes that we like to work with are going to be square root functions and reciprocal functions. So square root of x square root of x looks exactly like a parabola, except sideways. Base point 0, 0, passes through 1, 1. Those are the only 2 key points I draw, or at least plot. And then the general shape, sideways parabola, half of 1 at least. And then our last one is our, so I think the book calls it the reciprocal function, which will generalize to rational functions. And then our building block is just the basic 1 over x function. So what does 1 over x look like? Some key features. So other than points, we're going to have asymptotes as well. So of course, x cannot be 0 since we cannot divide by 0. There's going to be a vertical asymptote at x equals 0. And then we're going to have the point 1, 1 and minus 1, 1.
What does UND stand for?
Sorry, UND is undefined.
Is that the same as DNE, or is that different?
They're slightly different. We use undefined more to describe things that like we cannot define 1 divided by 0. It's infinity. In calculus, it's better to describe it as an infinity. But does not exist. Once you get into limits in calculus, they're going to be, there's a difference between a limit going to infinity, which you might call undefined, and a limit that doesn't exist. Don't worry too much about it for now. I think at this point, you can kind of think of them essentially as the same thing. And so what's this guy look like? It is a hyperbola. So other than the vertical asymptote, there's a horizontal asymptote at y equals 0. But it just looks like this. So key points that you're looking for, let's just say these 2 points, 1, 1, minus 1, minus 1, and the vertical asymptote. Horizontal asymptote, keep track of as well. Should be an easy part of the graph to keep track of under these transformations. Okay, so let's keep these pages handy. And let's get into our transformations. So how do we want to build from these? We want to build broader classes of functions based off of those simple graphs that we drew. First transformation we have are called translations. So in all these, we're given some function. And so to build new functions out of this, translations are going to look like this. This corresponds to a horizontal shift h units to the right and a vertical shift k units upward. Be careful with the signs. Note that the h, if we're going to shift along the positive x-axis, it's a minus. But if we're shifting in the positive y-axis upward, it's a plus. This is essentially because this is a pre-transformation in some sense. We're really changing the domain, then applying the function. So in some sense, we're actually just shifting the domain. It's like we're, instead of shifting the graph to the right, you can think of it as shifting the axes to the left and keeping the graph where it was. It's kind of, it's essentially where that minus sign comes about. So for example, if we have our building block, let's start with x squared, and we want to graph something like this. Well, we can write it out. X minus 2 is going to go inside for x, and then we have a plus 1 on the outside. And we can FOIL that out if we wanted to, but for quadratics, this is what's known as vector form. It's better to have it in this form because we can actually identify where it shifts. What did I say? Did I say vector form? I meant vertex form, excuse me. And so let's draw the graph. Our parent function is x squared. So I'll graph that in green here. We have our 0, 0, our 1, 1, and our 1 minus 1. And we have our shape, our general parabolic U shape. And what do we want to do with this transformation? We need to shift right 2 and shift up 1. As a heads up, in general, the shifts, or excuse me, the transformations don't commute. So you have to make sure you've got the correct sequence of transformations to do. In this case, it doesn't matter. Translations will commute with themselves, meaning that it doesn't matter which step we do first. We've got 2 translations, a vertical translation and a horizontal translation. And it doesn't matter if I shift everything to the right 2 and then up 1, or shift up 1 and to the right 2. So these ones, we can essentially do either one first. And what you want to do is essentially just figure out where those 3 points go to kind of dictate your shape. We're not stretching, compressing, or flipping or anything yet. So the relative position of these 3 points is always going to be exactly this. What's happening to our base point? We can just start with this guy. We're going to go right 2 and then up 1. And then the relative position is the same. So to find our other points, from there I can go right 1 and up 1. And I can go left 1 and up 1. And that will determine my parabola. So this is our g of x, and our f of x we'll do in green. So I'll do all of the parent functions in a color, either green or pink or blue. And then our actual function I'll make sure to do in solid black. Let's do one more. Let's do the reciprocal function. So let's say we have f of x is 1 over x. And I want to graph g of x is equal to f of, let's say, x plus 1. And then let's say minus 2. So what's this correspond to? This is a shift down 2 and a shift left 1. So mind that minus sign. So I guess if I didn't mention it, other words for translation, we might just say shift. It's more common. Just by shifting the graph means translate, and vice versa. So we can go ahead and graph again. Our parent function, so our 1 over x, we had 1, 1, minus 1, minus 1. We had a vertical asymptote and a horizontal asymptote, both at y equals 0 and x equals 0. And then we went as a hyperbola and traced, or like moved close along those asymptotes. So that's our f. And how do we find our g? We perform those indicated operations. We can do that to the point as well as to the asymptotes. So when I shift down to, the vertical asymptote isn't going anywhere. Vertical asymptotes go off to infinity, and of course, if I just shift that down, it's going to stay in place. But the horizontal asymptote is now going to move down to. And we're shifting left 1, so the now vertical asymptote is going to move to the left. And that shift left isn't going to affect this horizontal asymptote. For rational functions, I like to start with these asymptotes because it's really kind of how we guided it and how we drew it, right? These curves just trace along where the asymptote was. The green ones did with the green asymptotes.
Do we need 2 asymptotes? Sorry.
What'd you say?
Do we need 2 asymptotes? Because I thought we just needed like 1 up and down.
I would say try to do both if you can, especially because the horizontal asymptote, at least for this function, is going to be important because it doesn't cross it. And you do want to maintain that shape. In many ways, what it's going to do is kind of dictate the shift of this reference frame. So our XY frame in the original one, we really just took that whole frame and shifted it left 2 and down 1. And now we essentially have this new grid here. And relative to that, we have a point at 1, 1. So relative to where they cross, I go over 1 and up 1, and then go left 1 and down 1. And so our graph will look something like this. Okay, our next transformations are going to be reflections. So again, we're given some function. We want to define g of x as f of minus x or Sorry, rewriting my letters. Minus f of x. This is going to be a horizontal flip. So other than a reflection, we might say the word flip. Both mean the same thing. Horizontal flip, other things we might say flip across the y-axis or about the y-axis. If I flip a function about the y-axis, it means we're flipping horizontally. The negative out front of the function is a vertical flip. Across the x-axis. So for example, if we have our parent function, excuse me, as square root of x, let me get a new page. I don't think we'll have enough space for the graph there. Let's graph a horizontal flip and a vertical flip. So let's see, let's do these in color since we got 3 graphs. So let's keep our f of x in green. Let's put a grid here. So our square root of x had our base point 0, 0, had a point 1, 1, and then went like a sideways parabola. Let's do our g of x in blue. The negative x is on the inside, so if we were to write that out analytically, our g of x might just be given as square root of minus x. And so our g of x, when I flip this horizontally, 0, 0 is still going to be 0, 0. Flipping horizontally, you can essentially just change the sign of all of the x values. So we had this point 1, 1. Keep the y value the same, make the x value negative. So negative 1, 1. And then we graph. So it's going to be our g of x. And then our h of x would be a minus square root of x. And a vertical flip simply means we just change all the y values to a negative of what they were. So our 1, 1, x value stays the same. The y value is now negative 1. Our last things we can do are stretches and compressions. Given a function f, this is when we have a scaling factor, a scaling constant c. either inside the argument or outside the argument. And as with the other ones, anything that happens inside the argument affects our x-axis. So this is actually going to be a horizontal compression by a factor of c. And outside, when it affects the y values, it's going to be a vertical stretch by a factor of c. So for example, let's say I have f of x is x cubed. Let's say x cubed over 8. And we just want to graph this guy. So in this case, I didn't tell you the transformation. And we're running out of time. I would like to do some difficult ones. So let's go through this real quick. If I don't tell you the transformation, you have to come up with the transformation yourself. We can write this in two ways. You can either think of this as a vertical compression or a horizontal stretch. So let's pick our base function. Our parent function is going to be x cubed. And how do I get to this function from x cubed? Well, we can either take x cubed and then divide by 8 or multiply by 1/8. Or we could write it as g of x over 2. Since our x cubed over 8, we could write as x over 2 quantity cubed. So how do we graph this? I don't know if we'll have enough vertical space since cubes get really big really fast. But we can plot at least our key points here. So our green's our parent function, just x cubed. And what is this saying? So this 1/8 says take all of my y values now and shrink them down by a factor of 8. One thing to check, so when x is 2, so for our parent function, our green function, when x is 2, my y value should be up here at 8. So what's going to happen when I divide that then by 8, it'll come down here to 1. 0, 0 stays the same. 0 divided by 8, still 0. Likewise over here at -2, -8, then I divide by 8. It'll just be -2, -1. The other way we can think about it is, well, what happens if I tried this horizontal stretch or compression? So the factor outside of x is 1/2. So if it were a positive, or if it were just a 2, then that means I would want to compress the x-axis and cut everything in half. But since it's a 1/2, that's going to stretch everything by 2. You want to kind of think the reciprocal or the opposite type things are happening, remember, when we have our transformations inside the evaluation. So this 1/2 is actually going to stretch the axes. It's actually going to compress the axes by a factor of 2, which is going to look like stretching the graph, stretching the function by a factor of 2. And so these points that we had, 0, 0, now I'm stretching, when I multiply the x-axis, or the x value by 2, well, 0 times 2 is still 0. But here I had the point 1, 1. And when we multiply the x value by 2, it'll go to 2. Likewise here, multiply the x value by 2, it'll be negative 1 times 2. We'll go to negative 2. And so it'll look same shape, just broader. Any questions on that? Okay, so let's do one compound one with all of these things thrown together. Let me take attendance here. So we will get to, on the schedule, we're supposed to do IC5 today, but IC5 is composition of functions, which we're actually not getting to until Friday. So we will try to get to that on Friday, but keep in mind, we also have a mini quiz. So we'll see what we can get done. Let's graph. Let's say f of x is square root of, let's say 2 times 3 minus x. We need to be able to identify all the transformations. We've got the 2 out fronts. Let's identify our base function first. Our base function, or our parent function, is a square root. The square root is something that's the primary operation that's going on. There's no rationals, no squareds, or anything like that. Everything else is plus and minus or times constants. And so what do we have? We have a vertical stretch. We have a horizontal shift. And we also have a minus x inside the square root. So it's going to be a horizontal flip. Now, we have to be careful as to what order we do these things, particularly these two. Whenever we're doing flips and horizontal translations, we can do them in 2 different ways, and depending on which one we start with, the order will change. So which one do you want to start with? I'd say we can start with the vertical stretch, since there's nothing else going on in the vertical direction. This 2 out front, it's not going to affect much, and it's going to be a fairly...
The Wi-Fi's kind of cutting out in like...
Yeah, it's cutting out for me too. Same.
Yeah, sorry about that. I think the connection's a little shoddy at the moment. Did you guys hear what I just said, or do you want me to repeat it?
Could you repeat it, please?
Sure. So we have our base function, and these are the 3 things going on to get to here. But we got to be careful of which order we do them, and particularly these 2. So the order of our horizontal flip and our horizontal shift, it's going to depend on, or it will change which way we shift and which way we shift based on whether we do the flip first or the shift first. So I want to start with the vertical stretch. Since there's nothing going on vertically other than that stretch, it's not going to affect things, any other things. So if we start with g of x, and we define our first step, our first transformation as stretch by 2, will be here. And now, what do we want to do as our second step? Do you guys want to flip first or translate? do the flip first. We'll have to be careful with this. So if I then in my next step, sorry, we want h1 of negative x. What's this going to be? This is going to be 2 of square root of minus x. This is a flip horizontally for step 2. And then our step 3, what do I have to do from the previous step to finish off and get to where we want?
Add 3.
So we got to be careful. We actually want to shift to the right. Because then we will have a negative, and now we're putting an x minus 3 in for x, which will simplify to that expression. Okay, so how do we graph this? Let's go through it real quick. We're a little bit out of time. We have our parent function. We want to stretch everything by 2 in step 1. So 0 times 2 is still going to give me 0. When I stretch my y value of that guy by 2, it'll stretch everything vertically by 2. So this will be our first step, our first transformation. Our second transformation then flipped everything horizontally. Let me change that point to make the axes relatively close to the same scale. And then our third transformation, I'll do in black. This was our final step, was to
I
take.
think you're stuck, like,
Huh?
totally.
Yeah, he cut out from. It's frozen.
Is it back yet? You guys with me?
Now we are,
Kind
I
of,
think.
Or left.
Kind of.
Yeah, you got cut off for a minute.
Yeah.
I'm getting a notification about my internet connection is unstable. Sorry about that. There's not much I can do, unfortunately. I think it's a Comcast issue. Which step were you guys on? You catch step 2?
Yeah.
So step 2, we just flipped everything. And step 3, I want to take now my previous step, my pink line, and now shift everything to the right by 3. So we have this point and this point. We're just going to shift those 1, 2, 3. And then this point 1, 2, 3. And so our final graph.
Cut out again.
So we shifted our points, base point over 3. Our other point to the right 3, and then just drew it. Any questions?